In this question, we're asked to verify a solution here to a differential equation up here. And this one is second order, so I have the second derivative of f equals negative pi squared times the original function f. So to verify the solution, I have to run it through the differential equation. I take the first derivative, and I'm using the chain rule here that produces a factor of pi out of these trig functions every time. And I get negative pi c1 sine pi x plus pi c2 cosine pi x, and then I do it again to get the second derivative. Now I've got negative pi squared c1 cosine pi x minus pi squared c2 sine pi x. And it's here that I have to recognize my original function in this expression. If I factor out the negative pi squared, it looks like I have f left over in parentheses here. So I get c1 cosine pi x plus c2 sine pi x. And that is indeed negative pi squared times the original function f of x. And we have verified the general solution works. So one thing I wanted to point out about the solution space here is that this is all possible wiggles with a period of 2, because 2 pi over the coefficient of x is 2, that have a midline of 0. So when you add together these sines and cosines, as long as they have the same period, you're always going to get a pure sinusoidal function. But depending on the choice of c1 and c2, that's going to change the phase shift of this thing and the amplitude. So to nail down which particular sinusoidal function we're interested in, we have to apply two initial conditions to nail down two arbitrary constants, and we'll get one pure sinusoidal function with a midline of 0. So let's go ahead and apply these things. F of 0 is equal to 0. So when I plug in x equals 0, I get c1 cosine 0 plus c2 sine 0. All right, but the sine of 0 is just 0. Cosine of 0 is just 1. And so I end up with 0 equals c1. So we've already found one of the arbitrary constants. So I'm going to take advantage of that and write down the f of x is now c2 sine pi x. And then I'll apply the second initial condition. F prime of x is going to be pi c2 cosine pi x. And I know that f prime of 0 is equal to 1. So 1 is equal to this thing evaluated at x equals 0. So that's pi c2 cosine of 0, which is 1. And I end up with c2 equals 1 over pi. So I'll just move it down here. My particular solution to the differential equation has a c1 equals 0 and a c2 equals 1 over pi. So it must be 1 over pi sine pi x. In part C, we're asked to take a look at this and verify that it satisfies the initial conditions. So let's take a look at it. Okay, there's our particular solution. And I can see that it definitely satisfies the initial condition f of 0 equals 0 because it's passing through the origin. But how do we verify that it satisfies f prime of 0 equals 1? What I did was I just popped a tangent line into this at x equals 0. And I plotted y equals x to see if it was plausible that that was the tangent line. And that looks like this. So putting in a tangent line with a slope of 1 at x equals 0, I can see that it matches up really well and that the slope of this function is equal to 1 at x equals 0, so it matches that second initial condition as well. Finally, I should verify that it has a period of 2. So we have selected the one particular function with a period of 2 and a midline of 0 that passes through the origin and has a slope of 1 at the origin.